Hey, what's up, guys? This is Sheng here. So today, let's take a look at 1824 minimum sideway jumps. Okay, so there are like 3 lanes of roads of length n that consists of n plus 1 points and labeled from 0 to n. And a frog starts at point 0 and in the second lane. And the frogs wants to jump to the end of this lane. So, but there are like some obstacles along the way, right? And then you're also given like this kind of obstacles, right? Where the value of the obstacles represents which lane the obstacle exists. If the obstacle equal to 0, it means there's no obstacle at this point, right? So, and whenever the frog sees a obstacle, right, next to the current point I, the frog can jump, right? So he can jump to any of the lanes. So even if they are not adjacent, right? So which means that for in example 1 here, the frog were at this kind of lane 3 here, and he can jump to lane 1, even though there's like a obstacle in between, but the frog can jump. The frog can jump, right? And it asks you to return the minimum number of side jumps the frog needs to reach so that the frog can reach the last point in any of the lane, right? And so the constraint is like 10 to the power of 5, basically, right? So for this problem, right, I mean at each of the state, right, at each of the location, the frog has like some options, right? But one of the constraints that so if the next point does not have an obstacle, the frog can only travel from point I to point I plus 1 on the same lane. So which means that if the next one is valid, the frog will not jump. He will continue to travel until he sees like an obstacle, right? So now since the frog can be at any any point and at any lane, that's why we can define like a state of the frog, right? So which leads us to like a DP solutions, right? Which means that if we have a DP I and J, right? So it means that this one means what? At I point, right? And J lane, right? The minimum jumps, right? The minimum jumps this frog needs so to jump from this current from the I point and the J lane to the end of the road, right? So that if we define the state of DP in this way, we can just convert this DP problem into sub problems, So whenever we have a DP I and J here, we let's say for example, if the frog is at I and J, right? So if the next one basically if the next one is like a valid point, so the frog will just definitely jump to that location, right? So until the next one is not is an obstacle, then the frog will try to jump, right? But the problem is that when we see an obstacle, what are our valid options, right? Mm, so for example, right? Let's say this one. there are 3 lanes, right? So if this is the frog, right? Frog is here, and then the next one is obstacle, right? And then this one is not is valid, but let's say there's another obstacle here, and the frog is here. The frog is at the lane 3 here, right? 1, 2, 3. The frog can jump to lane 2 and lane 1, but it actually only lane 1 is like it's a valid one, because you know, if the frog jumped to lane 2 here, it doesn't make sense, because even though he jumped to lane 2, this is not a valid scenario, because after the frog jumping to lane 2, there's no way the frog can continue, right? Because the reason the frog wants to jump is he wants to continue. That's why, you know, when we trying to check the next the sub problems, we have to check both the current I and the current I plus 1 value. If only when both I and I plus 1 are not an obstacle, then then we can just ask the frog to jump. Okay. So yep, so that's the basic idea. You know, we just define the DP, and then we just try to find a valid sub problem from the current state, and then we just use the DP to solve it. Okay, so let's try to code these things here. And so we have like LRU, right, and the cache none DP. So we have a I and J, right? So I'm going to use the point and the lane here, right? And then we have n equals to length of the obstacles, right? And then we simply return the DP of starting point, which is starting from point 0, and then we end at also start from the lane 2 here. Okay. So to implement this DP, I implement this DP in a little bit different way here. Basically, I try to check if the current one can be, if the current, we can continue at the current lane, right? Basically, I check if the current while point is smaller than n and the obstacles, right, of point does not equal to the current lane, right? So this means that, you know, I'm trying to see if the current one is not is there's no obstacle at the current lane, then I just move the point forward by 1, right? Okay. So and here I check, right? Basically now the point is pointing to the either to the obstacle, right, or it's pointing outside of the lane. I mean, which is here, right? That's why, you know, I'm going to decrease the point by 1, and then I simply check if the point is equal to n minus 1. Okay. So if the point is equal to n minus 1, I simply return 0, because it means that we have reached the end of the of the lane here. So we can simply return 0. Otherwise, you know, otherwise I just do answer equals to system dot max size, since we're getting the minimum, right? And then I'll basically iterate all the lanes here. So I'll just use like a new lane, maybe in what, 1, 2, 3, right? And I check 2 things. If the obstacles of the point does not equal to the new lane, right? And the obstacles of the point plus 1 does not equal to the new lane, right? Then I would just do this recursive call, right? Because that's going to be the valid sub problems, right? 1 plus, since we need to make a jump, right? That's 1 plus dp point plus 1, and then the new lane, right? So this one will also cover the current lane, because for the current lane, you know, we know that, you know, the point plus 1 is definitely an obstacle. That's why it will not continue at the current lane. Right. So I think that's it, right? I mean, in the end, I will simply return the answer. So if I run the code here, yeah, LEN here, submit. Cool. So it passed, right? So as you guys can see here, right? So the time complexity of this one is what? Is the number of the states. So what is the number of states? So we have n points, right? Let's say we have n points. So it's going to be n times what? Times 3, right? So the lane is 3. So in total, it's 3n basically. You know, the and this one is like it's like a constant 3, right? That's why we have another 3 here. So in total, it's still O of n time complexity, right? Yeah, so that's the DP solution, where basically we simply define like a two-dimensional state here, you know, and at each state, we'll try to find a valid path. So first, we'll find like the blocking, the stopping, the obstacles. Otherwise, we'll keep jumping forward until we have see a obstacle, and then we'll try to find a valid path, right, among all three lanes. Actually, among the other 2 lanes, right, and then we get the minimum out of it, out of all the possible scenarios. Okay, so that's the first one. Now, actually, there's another solution for this one. Basically, you know, since we're getting the minimum number of side jumps, you know, we already have the state defined here. You know, we can that makes this problem like a good candidate of BFS search, right? So because with the breadth first search, it's by nature it can give us the minimum uh, steps, right, from the starting point to the end point. That's why we can just use like a BFS search. And so the key of using the BFS search is that to define the state, right? And we already have defined it. So the state will be the point plus the lane, right? So with BFS search, you know, we have a template, right? So the template will be what? First, we're gonna define like a queue, right? So for the queue, the starting point is 0 and 2, right? And then we're gonna have like a visited scene set, right? So that, you know, we will not revisit the same state again, right? And at the beginning, we also need to add this kind of the initial state to the scene set here, right? And then we're gonna have like also we need n here, right? The length of the obstacles, I believe. And then the remaining it's just like the template, right? So of the BFS search. So we have this kind of thing in range of length of Q. And then after each for loop here, you know, we increase the length by 1, right? And then in the end, I return the answer. Actually, I don't even need to return the answer here, because we will return the answer, so, you know, in the for loop here. Okay, so to do the BFS, we're gonna have like current point and the current lane here, right? Gonna be the Q dot pop left, right? So similar like how we explore the next states or the next sub problems in the DP solution here, we're gonna do the similar thing here. So first, we're gonna do this, right? I'll just copy this code snippet here, you know, because we'll probably most likely using the same logic here, which is the point, right? So with the current point here, and then with the new one, if it's not equal to this current lane, we'll basically keep moving forward, right? And then we're going to decrease it by 1. Similarly, when the current point reaches the end of the lane here, we'll simply return the answer in this case, because the answer will be the current step, which means is the jumps, right? Otherwise we're gonna copy and paste the same thing here, right? So I'll just use this one here, new lane here. So, and we're gonna have like the current point and the current point, right? But keep in mind that since we're doing the BFS search, that's why we're gonna need to add a third condition here, which is to check if the next state has not been visited before, right? So which means we're gonna have a current point and the current point plus 1, right? And then the new lane, right? So not in scene. Then we're gonna do this kind of q dot append of this new state, right? And we're gonna also add this new state to the scene set, right? So keep in mind that we're doing this when we are adding the new state either to the sub problems or to the queue. We're doing this current point plus 1. And why is that? Because once we jump to a valid scenarios, because we already check the next one, the current point plus 1 is like is not an obstacle. It means that for this valid sub problems or valid branches scenario here, the frog can definitely jump at least one step forward. That's why for the next new state, right, we're gonna do a current point plus 1 instead of current point. Actually, so even though you're doing a current point, I think it will still work. Yeah, I'm just simply doing this one to make it jump forward by 1. But I think current point should also work. So yeah, so let me try to run the code here. Answer, okay, 0, accepted. Yeah, so it also works. Let me try to change this one to current point. I believe it should also work. Uh-oh. Okay. Sorry. My bad. I believe this one does not work. Oh, this one. Maybe here. Okay. Yeah, so it also works. Yeah, I forgot to change the state, right? In other places. Yeah, so basically that's the second BFS search solutions where we find the at each of the state, right? We'll find all the valid next states. Similarly, like how we find the sub problems in the DP solutions here, we also try to keep jumping forward as long as it's a valid jump until we have reached the obstacle, and then we'll just branch out into different scenarios, and then while we're doing that, we're also gonna add this kind of a BFS template where we need to check if the state has been seen before. Otherwise, we'll end up in the infinite loop, right? In terms of the BFS traverse. Yeah. And other than that, it's just like the exit point, which is the current point has reached the end of this road, and that's when we will return the answer. Right, and the time complexity for this one is also O of n, right? Because the total state we are going to push into the queue is also 3 times n, right? Similarly, like what we have in the DP solution here. Yeah, cool. I think that's everything I want to talk about for this problem. And yeah, I'll just stop here. Thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.